Okay, so welcome everyone to the next seminar. So today we have a very exciting talk about some new results which are coming from the PandaX dark matter experiment, although maybe not exactly about dark matter in this particular case. So today it's very nice to have Ning Zhou, who's coming from Shanghai Jiao Tong University, and is going to tell us about these very interesting new results. So thanks very much for taking the time to be with us, and I will hand over to you. Thank you.
Okay, thank you very much. So it's great here to share our latest results about this exciting boron 8 neutrino 7th signature. Okay, so so the coherent scattering, as we all know, that was proposed in 1974. It described a process that neutrino elastically scattered off a nucleus. We exchange a neutral current. Later, we know that it is a Z boson, and the nucleus recoils as a whole. And the shortly after the Z boson discovery, uh, Drucker, uh, Drucker and Stodowski proposed the idea of using the seventh signature to detect the neutrino. And this coherent scattering happens for some specific with condition. For instance, if we can simply compare the neutrino de Broglie wavelengths with the nuclear size. For instance, if the neutrino energy is roughly 50 MeV for a medium-sized nuclear, then the neutrino will treat all the nucleus all together, and the amplitude scattering of each nuclear can be summed together, so that the scattering cross-section can be significantly enhanced. So the total cross-section can be seen here would be proportional to the number of neutrons square. And for the xenon case here, the similar like the cesium, it has a similar number of neutrons. So that would be very great, great advantage for these neutrino searches. And if we compare the cross-section with other interaction, for instance, the inverse beta decay, that's the interaction for neutrino discovery. And we see that for the 20 MeV neutrino energy, and the seventh cross-section could be even two orders magnitude higher than IBD. So does it mean that we can easily discover or use this seventh to detect neutrino? Probably not. That's the reason that the signature is very tiny. They transfer only tiny energy to the nuclear and get a nuclear recoil. So that requires that for instance, the kinetic energy of the nuclear recoil for the xenon or the argon or silicon is only like 10 keV. It's very small energy. That needs an ultra-sensitive detector capable of sensing such tiny nuclear recoil energy. So given this kind of challenges, the seventh process was only first observed 30 years after the proposal in a spallation neutron source at Oak Ridge National Lab by a coherent experiment. And this was published in Science. That boosted the that give us the confidence to search for this seventh in other experiment. And in 1985, the Goodman and Witten recognized that such a sensitive detector were well suited for searching for dark matter collisions with nuclear. And that's the incoming dark matter from the universe. And with like 220 kilometers per second speed velocity, and it's scattered with our nucleus, it will also produce such kind of a coherent scattering process, and that can be searched by such neutrino detector. And this sparked a 4-decade-long global race of underground dark matter direct detection experiments. And for instance, in the past decades, and the dark matter source sensitivity get improved by several orders of magnitude. And and our PandaX is one of the players. So here is our collaboration. The PandaX is a short name of Particle and Astrophysical Xenon Observatory. And it has around 90 members. And our experiment is located in the China Jinping Underground Laboratory. That in the southwest part of China, there is a tunnel inside the mountain. The tunnel was originally designed for the hydropower factory. And it is the deepest underground laboratory with 2,400-meter stones up the overburden. And another advantage is that it has a horizontal access, so that allow easy transportation to the laboratory itself. Okay, the detection or experiment principle is a timing projection chamber, as shown in this left plot. So the incoming dark matter collide with the xenon nucleus, and it produces the transfer energy, and the energy is immediately transferred into a scintillation light. That's what we call the S1. And at the same time, it produces some ionized electrons. And we give a strong drift field. So the ionized electrons drift upward to the gas phase of the xenon, where we assigned a much stronger extraction field, electric field. That's like 6,000 volts per centimeter. And there, the electrons signal was transferred again to delay the scintillation light. That's what we call the S2. And based on the S1 and S2, we can reconstruct the recoil energy and the position of the recoil. And furthermore, the ratio of the S2 and S1 can provides the discrimination power between the electron recoil and the nuclear recoil signatures. And our experiment started in 2009. Now almost 15 years passed, and we constructed 3 generations of detector from 120 kilogram xenon to now to PandaX-4T that contains 3.7 tons xenon in the sensitive volume. And at the same time, in order to increase the sensitivity, we have to lower the radioactive background further and further, so that the increase the volume and the lower background promise the good improvement on the sensitivity. And our PandaX-4T detector is further protected inside this shielding tank. That is the 900 cubic meter high purity water to shield the radioactivity from the laboratory itself. And the stone can shield the cosmic ray. But the environment in the laboratory also have lots of radioactivity. Okay, here is the picture of our detector inside the high purity water. So our experiment started the data taken started in the end of 2020, and we accumulated around 90 days data for the commissioning and to understand the detector performance. Then we noticed that there is some tritium leakage inside the detector, inside the xenon. So we recuperate the xenon for the tritium removal. Then we start the physics run in the end of 2021, and the run last 164 days. Then the CJPL, the underground laboratory, performed the construction and to reduce the radon emanation from the wall, etc. And we have to stop the run and recuperate the xenon and try to reduce the tritium further and upgrade the detector after the physics run and after the condition. For instance, we upgrade the PMT readout of the basis. And right now, we resume the new physics run and hope to catch up with other experiments like the xenon NT and LZ. Okay, the our first results is all based on this commissioning round, the round zero. And the question we want to ask besides the scattering the dark matter nuclear scattering cross section, we want to ask how dark is the dark matter? And like some neutral particle or even some, since we even don't know dark matter is elementary particle or composite particle, there could be some residual weak electromagnetic properties, and that can have couplings with the photons, like millicharge, charge radius, the electric dipole, magnetic dipole, antipole, etc. And the interaction through the photon with the nuclear or with the quark, the Lagrangian can be written here. That includes some high order loop level interaction. And the nuclear recall spectrum from the different electromagnetic property dramatically differs from each other, as seen from the left plot, and that's for different color for different the EM property and different masses, and so that we can search for we can have dedicated search for each of these EM property. So here are the results, and we have the first experimental constraint on the dark matter charge radius. And if we compare that with the neutrino, that is even 4 orders of magnitude smaller than neutrino. And for the other EM property, we improved from previous experiment by 3 to 10 times. And this was published in Nature. And after run zero, and we have the first physics run. The total exposure is 1.5 ton a year, and actually run zero is around 0.5, and run one is 1 ton a year. We double the exposure. And this is the electron lifetime monitoring as shown in this plot. So our the drift distance, the drift time from the bottom of the detector to the top, the gas region is around 800 microsecond. And we make sure that our electron lifetime, that's the parameter monitoring the purity of the xenon, or how much electrons is observed by those negative electric elements like the oxygen, water, etc. So that's give our good run list. And I said that between the run zero and run one, we recuperated all the xenon and performed offline distillation, and we successfully reduced the tritium background, as shown in the right two plots. The tritium is shown in the green in the orange histogram. That's as a function of the S1. I see that's produce the big excess in the low energy region. And from run zero and run one, we reduced by almost a factor of 10. And but there is still some left as shown in the bottom plot. So from run one to the run two, the run two is now we are starting, and there is the additional tritium removal campaign have been performed. And from the 0 to round 1, we built a more accurate detector response model, and we monitor the access the uh, we use a single energy physical event to monitor the response of the detector, like if there is some degradation of the PMT, the PMT, or if there is any level adjustment, the liquid level, the fluctuation during the run, and so that we correct the detector response for each run, and we have more accurate signal model by using using the electron uh, electronic recoil calibration and the neutron calibration with more statistics. And we also optimized for the signal reconstruction and taken and selection so that the eventually giving us higher signal efficiency. And with this improvement, we successfully improved our sensitivity from the previous round 0 result. That is the from this plot, that's the black line to the red line is almost a factor of 2. The lowest excluded cross section, the spin independent WIMP nuclear cross section is now it was 1.6 times 10 to the minus 47 square centimeter at 40 GeV. And for the high energy, the high mass part, like above 100 GeV WIMP, is surpassed the previous LZ result. And we know that recently, just last month, LZ released the newest result. The strongest constraint on the cross section now reached the 2 point around the 2 times 10 to the minus 48 square centimeter. That's a big success of the community. Okay, so that now we keep improving the sensitivity further and further down, but that was the end. And this is the neutrino fog, and the one actually is calculated by Syria. That's the after reaching the neutrino, or the seventh process is kind of irreducible background to our dark matter search, and we cannot distinguish this kind of events from from dark matter. And the neutrino fog coming from this solar neutrino, the left part for the small mass part, and the atmospheric neutrino, that's for the high mass part. And due to the flux of the solar neutrino, that our sensitivity, the xenon detector, that the first neutrino flow to be touched is here for the dark mass around 5 GeV. And actually this part, this 5 GeV dark matter signature is can be mimicked by is similar to this solar boron neutrino. The fusion reaction in the sun released an immense number of neutrinos. And the hotter end of the neutrino spectrum is dominated by this by those produced through the decay of the boron atom. Here, that's the neutrino energy is around 10 MeV, and the flux is not small, so it's that's why we can see the shoulder at this neutrino at the neutrino fog. Okay, so the nuclear recoil energy from the boron neutrino is so the seventh signature, as said, that is quite small, and showing in this plot for that's the pink one, the pink dashed one is the boron 8, and we see that the recoil energy through in the xenon is only several several keV, and the most parts of the below 1 keV. And our traditional 1 per hour energy threshold, as shown in the right plot, we can see the energy threshold is around 5 keV. This is the neutron nuclear recoil. So that we need the low threshold detection mode from the xenon detector in order to have a good efficiency to search for the boron and neutrino. So there are several approaches. After many years development, we know that we have attempted two types of low threshold detection modes. One is using the paired the region of interest. That's we have the S1, S2 paired events, but have and reduce the threshold of the S1 signal, and I will describe later. The other one is the ionization only region of interest. We call the S2 only. And as can be seen from the top plot, this is the coverage of the paired and S2 only events, S2 only region of interest, and the x-axis is the energy. We can see that the S2 only can have the lower threshold. And here the PandaX in 2023 performed such analysis. The left one is for the boron 8 search. The right one is was optimized for the low mass dark matter electrons recoil signatures. And the challenges, the lessons learned from these two analyses, that it's really crucial to control the background and build the signal model. Okay, for instance, let's start with these paired events. And the tradition, in the WIMP search, we have the S1 threshold at 2 PE. Now we can lower it down to as low as the 0.3 PE, the photon electron, and require the 2 hit or 3 hit events. That means that we require that at least 2 PMTs received the signals in order to beaten down the dark noise of the PMT. And in this way, we managed to reduce the detection threshold from like 5 keV NR down to 1 keV here. But the background is totally is dramatically dominated by the accidental paired events. These are non-physical events. It originates from the accidental paired isolated S1, S2 in a signal window. For instance, we have the signal window around 1 millisecond. If there is the isolated the single S1 or single S2 randomly pile up inside the signal window, then it mimic this mimic our the boron 8 signals. And this S1, S2 are all very small. So in order to monitor this, in order to model this background, we measure the isolated S1 rate and the isolated S2 rate, and randomly pair them in the window and perform all the quality cut after it, then give this accidental background contribution. And further, we need to validate this approach. The strategy is through this off window region, and this is the drift time of the selected events. And we know that the physical event drift region is not longer than 800 microseconds, and this big peak means indicates the place of the cathode. The cathode electrode is in the bottom of the TPC. And but there are still lots of events, lots of paired events with the drift time longer than the physical allowed region. That means this we call the off window. That is definitely from this accidental paired event. And since it's accidental paired, the spectrum, the distribution of this drift time is flat throughout is flat throughout all the signal throughout the event window, so that we can we can derive the normalization of this normalization of the accidental from this off window. And that's the comparison of the S2 spectrum is showing here. That's between the real mirror, the simulated accidental events and the off window events. Okay. And further, after the modeling this accidental, we developed the boosted decision tree to suppress this background. And we construct 23 variables based on the shape and the position of the events. And for instance, the top left one is the charge over the width of the S2. And we see that the simulated boron 8 is significantly different from the accidental. That's because in the accidental, there are some the origins of this single S2 have the different drifting distance. The actual drifting distance that may happen from the electrode, the cathode, or from the gate electrode, etc. Okay, with this boosted decision tree, we have this boosted decision score, and this is from the one hit sideband region. That's the same as the RY, but require that the S1 only have one hit. That's definitely it's dominated by the dark rate of the PMT, so that we are confident that this kind of sideband is a typical accidental sample. And the distribution of the CPPC score is shown here. Our modeling is well matching the data, and after the BDT we're able to suppress the accidental background by a factor of more than 100. For the one hit is the suppression factor is even larger, is almost 1,000. And here is the unblind result for the paired events. We have the 1.25 ton year, and this is distribution of the prediction score of the round 0 and the round 1, and the shadowed region is the ROI, and that is optimized by the S over square root B. Optimized by the S over square root B. And we didn't use this spectrum, the shape, to do this analysis. Instead we use the cat and the count. That's simply we want to have very conserved. We want to conserve the modeling of the systematic uncertainty. And here is the unblind data. In the round 0, we observed 1 events, but we expected like 2 events in the 2 hit region. In the round 1, we observed 2 events, and we expected the background applies the boron signature is around 3. So there is some downward fluctuation in this paired event selection. Okay, we continue with the second mode, that is the S2 only. mode, so that the threshold of the detection threshold is dominated by the S1 requirement. That's simply because that S2, this ionized electrons get amplified inside the gas region, so that the it is the S if we abandon the requirement of the scintillation light, the immediate scintillation light, the S1 signal, then we can reduce the threshold down to 0.3 keV. That's a big, that can save a lot of the boron efficiency. But the problem is that in this such a low energy low threshold mode, the background modeling, even the background modeling is a problem. This is an example of our PandaX-2 data searching for the S2 only signature, and the right plot is the xenon 110 for the S2 only. We see that the black dot is the data. They are all well above the background expectation. And even in the Panda, when even for this kind of for these two searches analysis, without the background modeling, we can only set a very conservative constraint on the dark matter signal. So only in the PandaX-4T round zero analysis, even though that was optimized for light dark matter candidates, we have built complete background modeling for the first time in the xenon detector. And we identified the two instrumental backgrounds. The one is called the micro-discharging event. And you have a strong dependence on wrong condition. This plot shows the rate, the small S2, the small single S2 rate as a function of the running time. And we found that in a short time, like in a short period called Z3, the S2 rate increased almost by a factor of 100. We know that at that time we are adjusting the high voltage of our electrode. So that in this 2023 analysis, we successfully built a data-driven the modeling of this micro discharging event. And the other one is the blue. This blue one is kind of a flat spectrum. That is the cathode events. And we found that the originating from the bottom of the TPC, since you have a very large width. And in this new search and in the round zero and the round one combined analysis, we developed a better micro-discharge modeling. And we have two types of samples. One sample is from the built contained events from the high S2 rate runs. The other one is built from the events vetoed by afterglow cut. That can be seen from the top plot. So usually in the detector, if there is a large S2, that's the detector become quite busy after it. And this is we call the S2 density as a function of the time after the larger S2. We see that the density, the S2 density is kind of exponentially decreasing then to some kind of quiet level. And that's the red line. And for instance, in this analysis, we simply remove those time like 50 milliseconds after the large S2. That's what we call the dead time. And but inside the dead time, we select those events, and that can provide very interesting information. And we found that in this high rate run, the S2 spectrum in both the here just put the here I put the n electron, that is the S2. We convert the S2 charge into the number of electrons, and since we measure the electron single electron gain, this parameter, so that we can convert the charge into the number of electrons. And we see the spectrum, the n electron spectrum are very similar between the daytime and the lifetime. And also the S2 width, the width of the path shape are also very similar. We also check the other parameters, variables that all have very consistent distributions. On the other hand, that we found that these samples selected in even it's like 30 milliseconds after the larger S2, they have a very strong position correlation with this large S2 signal. You can see here, this is the delta X distribution to the larger S2. So that we can pretty we have some conclusion that this kind of micro discharging events are actually the delayed electron emission after large S2 signal. And this the daytime sample has a much larger statistics, so that provide a very good modeling for this MD background. Okay. For the other one, for the cathode background, that's the electron emission from cathode because they have larger charge and a larger path shape width. So in the paired events, as shown in the left plot, it has a sharp peak in the drift time. And for round 0, we have 2 peaks. That's because we adjusted the liquid level and the drift field. And in the round 1, there is only 1 peak. So that we use the paired S1 as paired cathode events to model this model this S2 only cathode events. And it has a flat spectrum in the n electron distribution. And the spectrum is the shape of the spectrum is insensitive to the S1 selection. So that we can see that even for the S1 smaller than 10 p, the shape doesn't change much. And so that we can confidently model this without S1 cathode events through this paired events. Okay, so with this background modeling, and we did the optimization of our selection for this boron signal. And we require the n electron between 4 to 8. And the detection threshold is around 0.33 keV. And compared to previous analysis, the signal efficiency, selection efficiency is significantly improved. Previously, it's only like 15%. Now it's almost doubled to 30%. So that we can unblind this S2 only region of interest, the S2 only signal region. After unblinding, we see that we observed a significant excess, and it can be fitted by this boron CEvNS signals in both the n electron distribution and the S2 width distribution. But there is some upward fluctuation. And the fitted boron signal number of events is higher than the the one calculated from the the calculated events. And so that means then first the immediate question we ask that if we model the signal response correctly, and for such low energy deposit, how many electron the S2 how large how many S2 can be produced and how many paired events can be produced. So that needs the some calibration of the detector. But we have the MB and the deuterium-deuterium-neutron calibration, but that only cover the neutron recoil energy above around 5 keV. So below that, we don't have calibration. So that we have to rely on the global measurement. The next collect all the global data and give a give a fit to the data and assign a larger systematic uncertainties. Actually, in the Xenon N-town, they also uh, they have some very low energy neutron calibration that's showing the red band, the red from Xenon N-town. And but the that's for very low drift field in their detector is our drift field is almost 4 times stronger than than the than theirs, and so that's just only provide some reference for that. So we rely on the global data and perform a combined fit on both simultaneous fitting on the paired and S2 only uh, sample. And with this large yield and charge yield variation fully anti-correlated. Since if we reproduce the more scintillation light, then the Born signal will shift into the paired events from this S2 only events. So that have the charge, especially the light yield or the charge yield, have there is a strong anti-correlation between these two samples. And the solid line is our best fit last year charge yield from the on the Born signal from the Born signal fitting, and our best fit value tend to have a higher charge yield than the next nominal value. Okay, so here is the combined results. We performed the combined bin likelihood fit on the paired and S2 only sample. And for the S2 only sample, we simultaneously fitting the S2 charge and S2 width with all the systematic uncertainties included. So the best fit boron yield is 3.5 events in the paired region of interest and 75 in the S2 only region of interest. So you then can be converted into the flux. The flux, the fitted is 8.4 plus minus 3.1 times 10 to the 6 per centimeter square per second. That is consistent with the solar model prediction. And we have the significance is around 2.64 sigma. It's slightly smaller than 3 sigma, so that we can't claim the evidence of this signal. But we in the PIR said that we use the first indication of this signal. And this result was accepted by PIR just 2 weeks ago. Okay, and that's just demonstrate that the xenon detector is kind of a multi-phase experiment. And we, besides the search for dark matter, and we are also searching for neutrinoless double decay from xenon 136, that's for the majority neutrino. We can also search the astrophysical neutrino. And furthermore, that it opens the possibility of supernova neutrino detection in our xenon detector. For instance, if the supernova happens 10 kpc away from Earth, and no, 10 kbps, it's around 10 kbps from the Milky Way, and we expect around 10-ish events in PandaX-4T experiment in a short period, like within 1 second. So currently we are working on it and trying to join this SNILS, this early warning system. Okay, the future plan of the PandaX is we want to build the ultimate liquid xenon experiment with more than 30-ton scientific volume and the xenon in the scientific volume, so that if we accumulate around 200-ton year exposure, and our the dark matter sensitivity can very close to the neutrino fog. And even for neutrinoless decay, that depends on how we control the radioactive background, and it can cover this inverted mass hierarchy, the mass ordering neutrino scenario. And the proposed letter of interest has already been sent to the China funding agency. And here is the diagram of the concept of our experiment. But in order to accumulate more than 30 tons xenon sensitive volume, it will take some time. It totally depends on when and how we can get such large amount of xenon, given the expense price of the xenon. So immediate stage we plan to build a 20-ton experiment. It has a total the 20-ton xenon in, and in the center volume is around like 50-ton, 15-ton. And here is the R&D of the detector, and that is the liquid xenon storage system has been constructed. Now we expect to get this 20-ton experiment online almost 3 years from now. And so now the R&D is intensively carried on. So here is the summary. And we are one of the new generation multi-ton xenon experiment. We have intense searches for various types of physics, the dark matter, axion, neutrino, and majority neutrino, and expecting more interesting results. And now the whole collaboration is working on this 20-ton experiment, and we hope to get it online in 2027. And we also welcome new collaborators. Thank you.
Thank you very much. So, any questions? You can raise your hand if you have a question. Okay, I will go first. So what's the most interesting of my questions? I'm just wondering, actually, having now heard a few talks by LZ and Xenon, they talk a lot about the procedures for kind of reducing the bias in their analysis. So Xenon has a blinding procedure, and LZ have this salting procedure where they introduce this sort of fake data. Maybe you just didn't mention it, but it seems like you don't have a procedure like that, or do you have a procedure like that and you just didn't mention it?
Actually we have the blind analysis.
Okay. So is there a reason you chose that procedure rather than the salting procedure? I know there's some debate about what is the best approach, but what is your philosophy?
Yeah, we performed just like the Collider group, the classic experiment, just modeled our background before opening the data,
Yeah.
then just compare the result. For instance, here you can see that there is user blind analysis. We see that the high mass part, there is some downward fluctuation for the WIMP search, and for the low mass part, there is upward fluctuation. It's kind of up down. It's yeah.
And that goes also for your solar neutrino search as well. This is a blinded analysis.
Yeah, it's also a blinded.
Yeah, cool. Um, the other thing I wanted to ask, I didn't quite follow, was these micro discharging events that you talked a bit about, these sort of low energy events. And I got so these are, if I'm understanding correctly, as written there, these are, you have a big S2 pulse, and then there's just some sort of smaller S2 signals which always come after these big signals, and that's what's giving you this excess of events on the slide previous to this in the low energy region. Is that correct?
Yes. Yes. Actually, the the idea that the the large S2 produced lots of electrons. I mean, actually, it's the large signal that produced lots of ionized electrons. Then some of the electrons got absorbed by the impurity of the xenon. Then they gradually released later,
Yeah,
and this kind of a period lasts almost like 50
yeah,
even longer than for milliseconds. Yeah.
yeah. And if you increase the window of that dead time, do those events disappear?
Yeah, it's become the less and less, and that will, of course, if we increase the further, that sacrifice our exposure.
Mhm.
And the other interesting thing that we saw that it's a strong, it has some correlation with the electron lifetime. That is so if we are able to increase the electron lifetime, that means make the xenon purer and purer,
Mhm.
that will reduce the amount of this micro discharge.
Yeah, yeah. And uh, do you know, or have you speculated that? So there was a slide before this one where you showed a similar result for xenon, where they had this excess of events. Do you speculate that this is the cause for them too?
This one.
Yeah.
This is the one time the all the results. So if you read that I read their boron 8 signal the paper that's still under review of the PIL. They claim that in the S2 only search that due to their online radon removal system, the S2 only the rate increased by a factor of 10, and they don't know why.
Mm.
So I don't see that could have this S2 only results in short time.
Mhm.
But probably LZ could have the next one since they have the
Mhm.
much larger exposure and
Mhm.
the detection is quite stable.
Mhm. Um, the other thing was, I mean, I think this is something that's easy to check, but I don't know the answer off the top of my head. But there is another flux of neutrinos that is low flux but higher energies, the HEP neutrinos.
Ah,
Do
yeah,
you include
that's
those in your model? I mean, there's not going to be many events, but maybe there'll be like one or something in one experiment.
we don't. Yeah, we don't. We haven't. Yeah, we haven't.
Because I think because
The
obviously the flux is much lower, but they extend to slightly high energy. So if your threshold was at a certain point, you may actually get not a negligible number of them. And I don't know, they're
that's
kind of
this
interesting
is
because they've never been detected. So it's interesting to maybe include them.
that's it. So now we have the threshold around 0.3 keV here.
Right.
I see
Okay.
that is the amount of the
Yeah.
boron is
Yeah.
much higher than the HEP.
Yeah. It's going to be quite small. Maybe it's less than one event for your current exposure. But anyway, for the future, that's probably something
That's
to,
true.
to
That's true.
maybe it'll be interesting. Um,
Mhm.
Yeah, regarding your future plans, so obviously the sourcing the xenon is problematic for the whole community about where it's going to come from, how expensive it's going to be. Um, yeah, you put your request into the funding agency. Does China have any advantages in sourcing xenon? I mean, China must produce some amount of xenon. Is there some way you could ask very nicely and they will give you a good rate on it if you want to do a
The
Chinese run
uh,
experiment?
that's the kind of originally we hope that this could happen, but as after talking with these factories, though they sell the xenon globally, they have
Mm,
the prices, the market price that won't
yeah.
change, that won't sacrifice their interest.
Yeah, okay.
So Yeah, but the good thing that the currently the price of the xenon decreased, had drops down to several years ago, and now the especially for the in the industry, the need of from the industry, like the chips, the needs decreases at this moment. So there is a not small amount of
Mhm.
xenon available in the market right now.
Yeah, well, that's promising at least then.
Yeah.
And so your letter of interest, did that state a target mass, or did you just take a minimum target
We
mass?
take we request like around 40 for around 50 ton
50.
total
Oh,
xenon. Yeah,
okay.
50 ton.
And now what fiducial would that be? Like just a little bit less, or
The 50 ton the finished volume would be like not all. The second volume will be around 40 ton,
yeah, yeah,
and the
okay.
finished volume will be decreased
Hmm.
further depends on how we. That's
Yeah,
around probably 30, something like that.
yeah. And your 20-ton R&D that you're doing at the moment, how much of that would then feed into the 40-ton or 50-ton scale detector?
So as you can see here, that there are lots of upgrades on the hardware part, like you use a more cleaner material, like you use this acrylic, low background acrylic, and the PMT size can be this will be shipped changed from this 3 inch round the round one into 2 inches square one. And so this R&D or this 20 ton will test these new technologies. And if everything is fine, and if there is some hint of dark matter or
Mm.
there are lots of condition, then we can upgrade, ask money for upgrade to like 50 ton.
Yeah. And are you pretty much locked in with PMTs and not the silicon photomultipliers? Is it PMT the obvious choice?
At the moment, it's still PMT since the dark rate for the silicon PM still needs some time
Yeah. Mhm.
to reduce for this xenon experiment.
Okay, so last opportunity for anyone else. Uh, oh yeah, Tarek, go ahead.
Yeah, uh, in one of your slide, you were showing the S2 only events for both data and both signal and background. And if I just add up the 8 neutrino events, it would add up to 43. But you are like your final result is saying that your S2 only data have had 75 events almost. How are you getting that? Like in one of your table, you had 25 or
Ah, yeah, this one. So
yeah,
here,
so
right?
if I just
Okay,
add these two number 25 and 18,
yeah,
this would add up
right.
to
So
43.
this is the expected number of events. That's based on this nominal last year's charge yield.
Okay,
Yeah. So that's we found and the nominal barometer flux,
okay,
the theoretical barometer flux. Then we found that our data have some excess in order to fit it so that the charge rate is increased, and also the best fitted flux is larger, is still higher than the theoretical prediction. So that's in total we have like 75 versus like 40 events.
okay, thanks. Yes.
Mhm.
And is it clear that that upward fluctuation has to be from the neutrinos and not from, say, like these like micro discharging events? I guess this is all in your background model, right? And these fits would come out, but
Yes, the you can see that the increase is the excess is throughout all the regions from
mm,
our eye is from 4 to 8, but
yeah,
the micro discharge is only in the
yeah, yeah,
first
yeah, yeah,
beam.
yeah, yeah. Okay. All right. Well, yeah, let's thank Ning again. So I will stop